The first topic is what is Laplace transform, and the second one, what is inverse Laplace transform, and the last one is application of Laplace and inverse Laplace transform. So let's say this is the application. So we will go by these three ways. First one is what is Laplace transform. We will discuss the properties of Laplace transform, the definition of Laplace transform, and we'll try to understand the insight of Laplace transform by solving some problems. Similarly, we'll try to discuss what is inverse Laplace transform, and the last one is why do we need Laplace and inverse Laplace transform. That is the application of these two parts. So Laplace and inverse Laplace transformation are actually needed to solve ordinary differential equations. We need Laplace and inverse Laplace transform to solve ordinary differential equation. So what is an ordinary differential equation? In Math 120 course, that is integral calculus and differential equation, in that course you have solved some problems which are of differential equation, ordinary differential equation. So, and in this course, that means in Math 120, this book has been followed there. So let me show this one. You might remember that in Math 120, you are familiar with what is separable differential equation, linear differential equation, exact differential equation. Also, you are familiar with homogeneous linear equation with constant coefficient. What is superposition method, annihilation method, and variation parameter. All of you have gone through these topics in your previous course, previous math course, Math 120. So let me show one example from here. Then you can easily recall whatever you have learned. Let's say we have this differential equation, and for solving this differential equation, what we need at first, we'll convert this differential equation to an auxiliary equation. Like, just try to recall that from this equation we have total two solutions. Depending on these two solutions, m1 and m2, we have found the general solution, right? These solutions may be real number. You can see m1 and m2 are not same but real numbers. So then we can have this solution. Let's say for the second differential equation, this one, we have total two values of m where the values are same. So in that case, we have the solution is this. And lastly, the solutions for m can be complex number, complex conjugate actually. So in that case, the solution will be like that. So you can remember from your previous course that we have learned somehow how to solve differential equations, ordinary differential equations. You can see on right side of the equations we have 0. So that means for this we can say these are homogeneous differential equation with constant coefficient. Constants are 2, 5, y, before y prime, and y double prime. So from this differential equation, if we are asked to solve the differential equation. Our target is to find the function for y. You can see the solution is a function. The solution itself a function. So you can see for this differential equation, we have the solution for y. So sometimes we may have a differential equation with initial conditions. And if we apply our previous concept, then we can easily solve this one. So my question is, can we solve these equations by using Laplace and inverse Laplace transform? If you need the answer, then I must say that, yeah, we can solve the same differential equations by Laplace and inverse Laplace transformation. So this is the application of Laplace transform. Okay. So before starting, we have to have the motivation that why do we need Laplace and inverse Laplace transform. So Laplace and inverse Laplace transform are actually useful for solving ordinary differential equation. And the ordinary differential equation may be of higher order. You can see this is second order differential equation. Second order. In exercise section, you might have, you can see this is of fourth order differential equation. So whenever the differential equation is getting of higher order, it becomes too difficult to solve with the previous method that we have learned in Math 120. But Laplace and inverse Laplace transform is the powerful tool to solve this type of ordinary differential equation that may be of higher order. And in research field, particularly in mathematics research field, these two things are very important. So let's start from Laplace transform. Okay. And for Laplace and inverse Laplace transform, you can go through the same book, that means Differential Equation by Danish G. Gill. So this book is again helpful because we are going to solve the ordinary differential equation. Maybe in your final exam, there will be no question from this part. Questions will come from Laplace and inverse Laplace transform. Okay. But for your further courses, you can go through the application also. And in this lecture, I will try to show one problem that is from application part, or we can say how to solve ordinary differential equation by using Laplace and inverse Laplace transform. So are you ready for that?
Yes, sir.
Okay. So let's start with this part. Here you can see that in chapter 7 deals with the Laplace transform, and inside this chapter there are some sections. So here you will also find the inverse Laplace transform, and you will find the technique how to solve the differential equations also. So for the final exam, at least I request you, please try to go through 7.1, section 7.2 and 7.3. Okay, at least try to go through the examples from these sections. No need to solve the exercise part. Just if you need to have the insight idea, then you can go through the examples try to solve the examples by your own technique. Okay, the technique are this one. The formulas are here. Go through the problems and try to mark the problems with these formulas. Then you will get the insights. So section 7.1, 7.2 and 7.3. These are enough for your final exam. Okay. So let's start with 7.1. In your BUX video, you might have seen that Laplace transformation is an integral transformation. So what is an integral transform? Integral transform is denoted by this. Integral transform is one kind of improper integral. So what is improper integral? You know that improper integral is one kind of integral where the lower limit may be negative infinity, upper limit may be infinity. In both the limits, lower and upper, there may be infinity, or there will be some discontinuous function inside the lower and upper limit. That means inside the interval. So this is the definition of improper integral. So what improper integral is, if you need to have a solid idea about improper integral, you can go through your previous course, Math 120. But no need to do that here. We just need this notation. Integration from 0 to infinity. This is actually one kind of improper integral. So we can also go through this playlist where I have discussed what improper integral is. Okay, so actually from improper integral we can expect two observations. The solution for any integral, let's say we have integration of x squared dx, integration from 0 to 3. The solution will be, the antiderivative will be x cubed over 3. So if we apply the fundamental theorem of calculus, then where we have x, apply the upper limit, negative 0 cubed by 3. So that means we have actually 3 power 3, that is 27 over 3. 9 is the result. Okay, so you can see we have found a finite number from this integral. So since we have found a finite number, finite value, that shows that the integral converges. Let's say we have an improper integral, integration from 0 to infinity x squared dx. So if we try to solve the same way, integration of x squared is x cubed over 3, upper limit infinity, lower limit 0. Actually, this is not the proper way to solve this one. We have to come up with the limiting concept, but for short overview, I am using with the same concept, that is with upper limit and lower limit outside the square bracket. So here you can easily see that at first we can go with upper limit, so infinity cubed by 3 and 0 cubed by 3. So that means this time infinity by 3, that is actually infinity. Infinity minus something, that is actually infinity. So the result is getting divergent. If we have a look on some other problems of improper integral, we can also expect here a finite number. So these are the cases that improper integral may be convergent, may be divergent. What is convergent? If the result is becoming a finite number, then we can say the integral exists or the integral is convergent. If the integral doesn't exist, you can see here we have the limiting concept. So if limit doesn't exist, then the integral is divergent. So have you understood this concept? Actually, I am starting from the very beginning part, so that's why it may be difficult to understand, but gradually you will get the things. But for the time being, please try to understand that any improper integral will keep us to conclusion. The result may be convergent, the result may be divergent. When we can expect convergent? If the integral gives us a finite value, then the integral is convergent. If the integral is giving us infinity or negative infinity or indeterminate forms, then we can say the integral doesn't exist and is divergent. So actually, Laplace transformation is one kind of improper integral, which is one kind of integral transformation. So from chapter 7, we can go through 7.1, 7.2 at least, and also 7.3 if you can. So 7.1, 7.2, 7.3. These three sections are very helpful for your final exam. So let's start with our first part. What is Laplace transformation? Actually, Laplace transformation is named after the mathematician Pierre-Simon de Laplace. So he was a French mathematician who first discussed the properties of Laplace transformation. And Laplace transformation is denoted with the curve L. We can say it is squiggly L. This is not this L. We can use this curve L. Okay. So Laplace transformation is named after the mathematician Pierre-Simon de Laplace. Before studying Laplace transformation, we have to know the definition. So what Laplace transformation does is that it transforms a function, a time variable function, where time is input, to another function with another variable s. This is the main thing. So any function f of t will be converted to another function f of s by using Laplace transform. So in short, we can write Laplace transform of any function is actually f of s. So Laplace transform is an operator where we need an input, and the input is the function f of t, and it will give us an output f of s. So this is the input. Input is itself a function of time, and finally we are getting an output. So Laplace transform of f of t is f of s. So actually these parts can be defined with the improper integral. So Laplace transformation of f of t can be denoted by f of s, but it is nothing but an improper integral. So the improper integral comes from 0 to infinity e to the power minus st f of t dt. That means we are integrating in terms of time variable. And see how s is coming, output is this one, output is f of s. That means we are integrating in terms of t, so automatically t becomes vanish, and finally we have the s variable. So we will get a result, let's say 1 by s square plus 1 or 1 by s square plus 4. The result becomes a function with s variable. So Laplace transformation is an improper integral from 0 to infinity e to the power minus st f of t dt. So this is the definition of Laplace transformation. Similarly, what is the inverse Laplace transformation? Let's say Laplace transform of f of t is equal to f of s. We don't need to write this integral again. Now, therefore, f of t equal to inverse Laplace transformation of f of s. So you can easily see that from the definition of Laplace transformation, we can also think about inverse Laplace transformation. So if Laplace transformation of f of t is f of s, then the inverse Laplace transformation can be defined by f of t equal to inverse Laplace of capital F s. So be careful about the letters. Small f is the main function, and capital F, that is big F, is the output with s variable. So what Laplace transformation does? Laplace transformation actually transforms the time variable function to another function, which is actually an algebraic function. What is algebraic function? Let's say we have x squared plus 5x plus 6 equal to 0. Like s squared plus 5s plus 6 equal to 0. So this is one algebraic equation. So Laplace transformation, at first, don't forget that why do we need Laplace transformation? Laplace transformation is actually needed to solve ordinary differential equation, like let's say dy dx equal to x squared. To solve this type of differential equations, we need somehow Laplace transformation. This is a powerful tool. So if we apply Laplace transformation to this differential equation, this actually may give us an algebraic equation like s squared plus 5s plus 6 equal to 0. And you know, dealing with algebraic equation is very easy for us. So that's why the advantage of Laplace transformation is Laplace transformation takes a function as input and converts or transforms the function to an output with s variable by using this definition, this integration from 0 to infinity e to the power minus st f of t dt. Now let's come up with the formulas of Laplace transformation. You can see whatever I have written here, Laplace transformation of f of t is f of s. So same thing is given here. Laplace transformation of f of t is capital F with s variable. So suppose we have Laplace transformation with constant. That means the function is a constant. So what will be the result? The result will be c by s. If we have the function as t power n, then what will be the result? N factorial over s power n plus 1. If we have the function f of t as e power at, then the result will be 1 by s minus a. So try to have a look closely that in left side we have time variable. You can see t is here, t. But on the right side we have s variable everywhere. S variable, like that. Laplace transformation of cosine kt is actually s over s squared plus a squared. Laplace transformation of sine kt is k over s squared plus k squared. You can see I have also mentioned here the hyperbolic cosine part and hyperbolic sine part. The relation, the similarity of cosine and hyperbolic cosine is, you can see that here we have plus and here we have minus. Similarly for sine and sine hyperbolic, plus, minus, but the formula is same. So Laplace transformation of a constant is constant by s. And here I have also mentioned the inverse Laplace transformation, that is f of t equal to inverse Laplace of f of s. So same thing is done here. F of t is inverse Laplace transform of f of s. So if we use, if we try to find the Laplace transform of a constant, we will get constant by s. Now suppose we have constant by s and we are using inverse Laplace, then we'll get c. So same part is here. You can see 1 by s minus a, 1 by s minus a. S over s squared plus k squared, s over s squared plus k squared. And we are getting the f of t function. So these formulas are helpful. If you have any problem in understanding the concept, then you can anytime ask me. Okay. So you might be wondered that how the result is coming. Laplace transform of constant is how c by s. Laplace transform of t power n, how can we expect this result? N factorial by s power n plus 1. How the result is coming for Laplace transform of e power at is 1 by s minus a. This is by using this formula. So all the formulas, whatever formulas I have mentioned here, so all the formulas can be obtained from the main definition. Okay, that means we can derive all formulas from the main definition. So let's work with the first one, Laplace transformation of constant, because by using the definition we can derive all the formulas, but in your final exam the problems will be you have to solve directly the problem. If definition is mentioned, like solve the problem by using the definition of Laplace transformation, then you have to use this integral. But if definition is not mentioned, you can go through, you can solve the problems by using the direct formulas. You can solve the problems directly by using these formulas. Okay, so let's say we are working with the first problem. Suppose we have a problem, find the Laplace transform of f of t equal to 1. What is our function? Our function is f of t equal to 1. The question may also be in this form. Evaluate Laplace transform of 1. So here I have written the two alternative forms of the question pattern. So if the question is coming just like this way, we have to find the Laplace transformation of f of t, which is equal to 1. F of t equal to 1. So we know the formula, that is Laplace transform of a constant is constant by s. So Laplace transform of 1 is 1 by s. That means Laplace transform of f of t equal to capital F of s. So see, by using the direct formula, we have solved what the result is. That means we will get full marks if we apply the formula. The mark may be 10, the mark may be 15. Don't be confused with the question pattern. But if the question is like that, find the Laplace transformation of f of t by using the definition, or evaluate Laplace transformation of 1, f of t is equal to 1. So evaluate the Laplace transformation of 1 by using the definition. Then the definition is this. There is no alternative way to solve by this one. So we have to use this integral. But if definition is not mentioned in your question, then this is your solving technique. So have you understood what I am trying to say?
Yes, sir.
So if definition is mentioned, then we have to solve by definition. So let's try to solve by definition. So we are going to solve Laplace transformation of 1. That means this is the function where f of t equal to 1 by using definition. So we know that by definition, Laplace transformation of f of t, you can see already the result is in our hand. But since definition is mentioned in the question, so you have to show the whole process. But this type of questions will not may not be in your final exam, because we'll try to avoid using definition, but sometimes there will be some theoretical problems, okay, theoretical questions. So that's why you have to also know how we can get the result by using the main definition. So Laplace transformation of f of t is actually f of s, so which is an improper integral 0 to infinity e to the power minus st f of t dt. So this is the definition of Laplace transformation. That means Laplace transformation of f of t is actually this one. So the function that is inside the curly bracket is f of t, and f of t is also on the right side integral. So now Therefore, Laplace transformation of which function? What is our function? Our function is 1.
1.
Okay, so Laplace transformation of 1. That means where we have f of t in the definition, we are writing just 1. This is our function. So equals 0 to infinity e to the power minus st dt, and the function is 1. Now we know how we can solve this integral. So let's try to solve Laplace transformation of 1 is equal to 0 to infinity e to the power minus st dt. Because if we multiply e to the power s minus st with 1, we will get the same part, e to the power minus st. So since this is an improper integral, so from the concept of math 120, we know that we can't solve this integral without the help of limit. So we have to take the help of limit. Let's say limit k, which is approaching to infinity, then 0 to k. It is an improper integral having lower limit a finite value, but the upper limit is infinity. Upper limit is unbounded. But we are trying in such a way to convert this improper integral to give a look like proper integral. Let's say this is 0 and this is a proper value. But actually, the value, that is the variable k, is approaching to infinity. So this part and this part is of same meaning. So if you still have any confusion how to solve improper integrals, then for your betterment, you can go through this playlist. I am giving this playlist here. Actually, I have made this playlist for Math 120 course in last semester. So in that part, you will see that this type of improper integrals can be solved with the help of limit. So infinity is being replaced by k. So e to the power minus st dt. That means this integral is here. But the extra part is coming, that is the limiting concept. And remember, Laplace transformation will always be convergent. It will not be divergent. It will be convergent. So that means we will have a result, and the result will be 1 by s. We have already solved this one directly. So let's try to solve theoretically. So now limit k tends to infinity. So you know the formula from integral calculus that integration of e to the power mx dx, that is nothing but e to the power mx by m, right? So we'll apply the same formula here, e to the power minus st dt. So that means e to the power negative st over negative s. And we have the limits of integration. Upper limit is k, lower limit 0. Do you understand how I am solving? Any problem up to here?
No, sir.
So let's try to solve. Limit k tends to infinity. Now we have solved in terms of which variable? We have solved in terms of time variable t. So upper limit will be plugged here in the place of t, and the lower limit will also be here. So that means in next equation we can write e to the power minus s k. That means t is replaced by the upper limit by minus s. Then negative e to the power s times 0. Okay, something times 0, that will give us 0. Negative 0 means actually 0. So e to the power 0 is here over negative s. I am solving just with the concept of integral calculus. I think you are understanding. So k tends to infinity minus s e to the power minus sk, negative negative positive, 1 over s. So now this is the time to input the k value. That means here we have k, we have to input this limiting value. So there will be two cases here. I have already mentioned that Laplace transformation will always be convergent. Laplace transformation is an improper integral which will give us a finite result. Okay, so if the result is infinity, it will be divergent. So one thing try to understand here, actually the result will be 1 by s, because we know the direct formula. Laplace transformation of 1 is 1 by s, Laplace transformation of c is c by s. But actually what process is working behind? That is the question. Try to understand. We are going to plug infinity here where we have k. That means e to the power minus s times infinity. That means e to the power minus infinity by minus s. Plus we have also 1 by s. So try to get the result here. E to the power minus infinity. Sorry, e to the power minus infinity is actually 1 by e to the power infinity, right? That means e to the power infinity is infinity. So 1 over infinity means something by infinity means what will be the result?
0.
We are getting 0 plus 1 by s. So that means this is how we have found 1 by s. Right? Have you understood?
Yes, sir.
At first, we have solved the integral. And integral with upper limit, negative integral with antiderivative with upper limit, antiderivative with lower limit. And now this is the time to input k as infinity. Here we have k, so e to the power minus s infinity, that means e to the power minus infinity. E to the power minus infinity is actually 0, so 0 by minus s is 0, so we are left with only 1 by s. So this is the result, how we are getting Laplace transformation of 1. Laplace transformation of 1 is 1 by s. Okay, see, we have the same result previously. Laplace transformation of 1 is 1 by s. So have you understood up to now?
Yes, sir.
So let's hope for the better. Let's solve the problems not by definition. Let's solve by the formulas whatever I have here. So from section 7.1, you can see some examples are here. Laplace transformation of 1 is 1 by s, and how 1 by s is coming is given here. Okay, so you can see when s is greater than 0, then only it is possible to get 0. Otherwise, we will get divergent value. So the problem has been solved using the definition, using this definition. So I will request you try to go through example 2, example 3. All these problems have been solved by using the basic definition. Process is same. But now we will apply these formulas to get the direct result, because in final exam there is 99% probability of this type of questions. So that's why we will solve Laplace transformation of e to the power minus 3t will directly be this one. So let's see how we can solve using the formulas. So all the formulas that are given here can be derived by using this integral concept. Okay, so without wasting time, let's solve some problems directly. So again, for your recall, I am writing the formulas of Laplace transformation. So the first formula comes with Laplace transform of a constant c is c by s. Laplace transformation of t power n, if the function is t power n, then it is n factorial over s power n plus 1. Laplace transformation of e power at is actually 1 over s negative a. E power at is 1 over s negative a. Similarly, Laplace transformation of, let's say, we have cosine kt, that is equal to s over s squared plus k squared. Laplace transformation of sine kt, that is equal to k over s squared plus k squared. Yeah. So also, if we have Laplace transformation of hyperbolic cosine kt, then instead of plus, it will be negative. Similarly, sine hyperbolic kt, instead of plus, we can use minus. These are the formulas for hyperbolic cosine and hyperbolic sine. Because from your previous weeks, from complex analysis part, complex variable part, you have learned what hyperbolic function is. Actually, hyperbolic functions are this one. Hyperbolic functions can be denoted by this. That is, sine hyperbolic is actually e to the power minus x negative e to the power minus x by 2. Hyperbolic cosine e to the power x plus e to the power minus x by 2. So these are the functions, what hyperbolic functions is. Okay. So let's solve some problems by using the formulas. Suppose we have Laplace transformation of Laplace transformation of, let's say we have cosine 3t. So what will be the result? Have a look on the formulas. Which formulas can be applied? This is not one. This one can be applied, right? Because here we have cosine kt. So the value of k is here 3. So k equal to 3. We know that Laplace transformation of cosine kt is s over s squared plus k squared. So similarly, try to respond this time. What will be the result here? Because this is important. I need this time your response, otherwise we can go to the complicated problems. What will be the result? S squared over s squared plus
So উপরে কি s স্কয়ার হবে?
it will be, sorry, in upper part it will be, thank you, it will be s over s squared plus 3 squared. That means the result is s over s squared plus 9. So Laplace transformation of cosine 3t is actually s over s squared plus 9. That means, again, compare with the basic notation, Laplace transformation of f of t is actually f of s. So automatically, whenever we are applying Laplace transformation in right side, we are getting a function of s, which is an algebraic function. So you will get full marks up to this. Let's say we have another problem. Suppose we have Laplace transform of e to the power negative 9t. So what will be the result? E to the power at. This formula will be applied. So try to note down the value of a. Here a is negative 9. So it will be 1 over, have a look on the direct formula, 1 over s negative a. So 1 over sorry for the inconvenience. Somehow there is a problem in network. So the result will be 1 over s negative a. So negative a. Try to be very careful about placing a. You know that e to the power at, Laplace transformation of e to the power at is equal to 1 over s negative a. So that means 1 over s plus 9 is actually the result. Have you understood?
Yes, sir.
So let's solve another problem. That will be also the easiest one. Then we can move to the complicated problems. Suppose we are going to solve Laplace transformation of sine 5t. So here the formula, out of these formulas, Laplace transform of sine kt can be applied. Okay, here I have forgotten to give an square. Yeah, k over s square. So Laplace transformation of sine 5t, the value of k is 5. So have a look here. Laplace transformation of sine kt is k over s squared plus a squared. So 5, that means k over s squared plus 5 squared. So that means we are actually getting 5 over s squared plus 25. So I hope you have understood up to this part. So this is our capital F S, because here we have a function with s variable. So now let's move to the complicated problems. Whatever problem we have solved here, Laplace transform of cosine 3t, Laplace transform of e to the power minus 9t, or this one. These three problems can be solved directly by these formulas. But now we have to take an advanced look that Laplace transformation has some properties. There are three properties actually. This is the linearity property. This is called the shifting property or translation property. And the third one is called the multiplication by t power n property. So there are actually three properties here by which we can solve some complicated problems. So we have actually three properties in Laplace transformation. If you have a look on the contents here, you can see operational properties 1, operational properties 2. So these properties are actually given in short here. So you can go through the book for the properties, or you can note down from here also. So let's solve some problems with linearity property. So what is linearity property? Linearity property of Laplace transformation. Suppose we have Laplace transformation of a f of t plus b g of t. So first thing first is that by the time we know that Laplace transformation of f of t, what will be the result in short on right side? Can anyone guess? it will be f s, small f, and in right side we have capital F. So let's say we have Laplace transformation of g of t. So what will be the result? Try to say small
G,
Fs, I guess, or G.
g of s. Let's say we have Laplace transformation of small y t. So what will be the result?
Y of S.
Y of
Capital
S.
Y of s. Again, let's say we have Laplace transformation of small x t. It will be capital X. So since we are the beginners, so that's why we are dealing with this type of symbols, small f, capital F. But things will be complicated if we go in further contents. So now Laplace transformation of f of t is f of s. So Laplace transformation follows the linearity property. Linearity property means if we have summation or subtraction, then we can write by this way. Laplace transformation of a f of t plus Laplace transformation of b g of t. That means what we have done here, we have just separated the summation term. The same thing goes for if we have negative. So it will be replaced by negative. So let's work with positive sign. And finally, we can write here a and b are constant. So a and b can be pulled out before the Laplace transformation. B Laplace transformation of g of t. Now, what we can write? A is here, b is here. Okay. Now the result will be Laplace transformation of f of t is actually f of s, capital F s. Laplace transformation of g of t is capital G s. So this is known as the linearity property. So Laplace transformation of this big function, inside the curly bracket we have a f of t plus b g of t. That means we have combination of functions, but the result can be easily found by these ways. And finally we have approached to the result. So let's solve some problems with linearity property. Then gradually we will move to the shifting property and multiplication by t power n property. Then we can say that is enough for Laplace transformation. And then we will try to have a look on inverse Laplace transformation if you have time. So I am here still
Yes.
1 hour time. So within this time I will try to give the short overview of these two topics so that you can have a good mark if you are solving Laplace and inverse Laplace transformation in your final exam. So suppose this time we have Laplace transformation of t squared plus 1 whole squared. So this time we have to solve this function. We have to solve this Laplace transformation. So try to have a look on the formulas. Okay, first of all, try to understand the question pattern. If I ask you, evaluate the following. Same thing, suppose we have Laplace transformation of t squared plus 1 whole squared. We have to evaluate by definition. So try to understand the question patterns. Same problem is given, but the solving technique is different. For this question, we can use the direct formulas, but for the second one, evaluate the following Laplace transformation by definition. So here we have to use the concept of improper integral. So this type of questions will not come, but try to understand how we can form using the definition. So we know that Laplace transformation of f of t is an improper integral from 0 to infinity e to the power minus st f of t dt. So similarly, here Laplace transformation of this function, the function is this one, t squared plus 1 whole squared so it will be just we can write similarly whatever we have previously 0 to infinity e to the power minus st f of t dt. In the place of f of t, let's write in the place of f of t, let's write t squared plus 1 whole squared. So try to understand. Here we have by definition one improper integral. So it is quite difficult to solve by using the concept of integral calculus. It will be also hard for me to solve this one, but we are lucky today that we have this type of formulas. So all these formulas have been generated, have been derived just for our betterment. So try to be 100% sure that this type of complicated problems, if these are coming in your question, in your final exam, this will not be with the definition. Okay? So have you understood what I am trying to say?
Yes, sir.
Okay. So let's solve the same problem. Let's solve the same problem by using the formulas. Actually, we can solve also by this definition, but actually it is going to be the research based question. So we don't need this one actually. So let's try to solve here by using this. So the formulas, whatever I have mentioned here, try to have a look again. Try to have a look on the function. We have t squared plus 1 whole squared. So is there any direct formula here? Have a look on the formulas. We have Laplace transformation of c, Laplace transformation of t power n, Laplace transformation of e power at, cosine kt, and sine kt. But there is no such formula like this one. Do we have? So do we have any direct formula that can be applied to solve this problem? Actually, we don't have. The formula that is closely going with this part is maybe Laplace transformation of t power n. But here we have t power is 2 plus 1 power 2. So what we have to do here, we can somehow simplify inside the curly bracket. We know a plus b whole squared is actually a squared plus 2ab plus b squared. Right? Have you understood?
Yes, sir.
And now, just before this problem, we have learned what is linearity property. Linearity property allows us to separate the summation or subtraction terms. So let's write Laplace transformation of t power 4, Laplace transformation of 2t squared, Laplace transformation of 1. Again, what we can write? We can directly write 2 before the Laplace transformation because 2 is constant. So I hope you have understood up to this part. Now it is going with the formula. So Laplace transformation of t power n, what is the result? It is n factorial over s power n plus 1, right?
Yes, sir.
The Laplace transformation of t power 4, let's solve the first one. It will be it will be 4 factorial over s power 4 plus 1. 4 factorial over s power 4 plus 1 plus 2 is here. And now let's solve this one. Laplace transform of t power 2. What will be the result?
2 factorial by s 2
S
plus
power 2 plus 1. And the last one, you know, Laplace transformation of a constant. The first one is constant by s. Have a look on the first formula. So Laplace transformation of 1 is actually 1 by s. So finally, you have to solve a little bit here, or you have to simplify some parts. So finally, what we can write? It is 4 factorial is actually 24, s power 4 plus 1, that is s power 5, plus 2 factorial is 2, 2 times 2, that is 4, s power 3 plus 1 over s. So see, every time the theory is true. That is, Laplace transform of any function with time variable will give us an algebraic function with s variable. So see, we have found the result. So this is actually capital F S. So have you understood this one?
Yes, sir.
So sometimes we may not have the direct formulas or the direct functions that are going with the formulas. So in that case, we may have to simplify the previous function so that we can use these formulas. So let's solve another problem. Suppose we have to evaluate Laplace transformation of e to the power negative 3t plus 5 cosine t. Okay. So this time the function that we have Don't forget the basic notation. Laplace transform of input is f of t. So the whole part is f of t. And finally, we'll get a function of s. So here, the function is looking difficult. It is looking a big function. But since we know the linearity property, so linearity property suggests us to separate this one. Since 5 is constant, so let's write 5 before the Laplace transformation symbol. Now, this is the time to focus on the formulas. So we have 1, 2, 3, 4, 5, 6, 7 formulas. So the first one, we have to solve this Laplace transformation of e power at. That is actually 1 over s minus a. 1 over s minus a. So what is the value of a here? A is -3. So the result will be 1 over s negative a. Be careful about the sign change. Okay. Plus 5. Laplace transformation of cosine t. We know Laplace transformation of cosine kt is actually s over s squared plus k squared. So it is cosine t. So what will be the result? Try to respond. First tell me what is the value of k here? Cosine kt, cosine t. So what will be the k value?
So cos will be the value of k.
No. Cosine kt. That means we actually have cosine 1t, right?
Yes, sir.
Yes, sir.
So the value of k is 1. Thank you for your comment, but actually we need sometimes response, otherwise we will not get the inside part. So here k is 1. Cosine t and cosine 1t is same. Remember, k is not cosine. K is just a number. So by this you can understand that k must be 1. So the result will be s over s squared plus k squared. That means s over s squared plus 1 squared. Have you understood?
Yes, sir.
So you will get full marks up to this. But let's try to simplify. So 1 over s plus 3, 5 times s over s squared plus 1. And finally, we have found a function which is an algebraic function like f of s. So I hope up to this part you don't have any confusion. Do you have?
No, sir.
So if you don't have any confusion, let's move to the complicated properties. this one, first shifting or translation property. Try to have a look that Laplace transformation of f of t is f of s, that is okay. Laplace transformation of e power at is equal to 1 over s minus a. But what if we have Laplace transformation of e power at and f of t? Then you can see the result is not f of s only, we have f of s minus a. Try to understand. Instead of f of t, this time we have e power at f of t. But despite having e power at, the result is not 1 by s minus a. So that is a thing to understand. Okay, this is called the shifting or translation property. If Laplace transformation of f of t is f of s, we know, then what will be the case for Laplace transformation of e power at f of t? It will be f of s minus a. So can you see the property from here?
Yes, sir.
So let's work with this property. So once you have a strong control over Laplace transformation part, then it will be easy for you to solve the inverse Laplace transformations. Because if you are able to solve the Laplace transformation problems, it will be far easy to solve the inverse Laplace transformation because it will be the reverse process. So first thing first is to know how we can use the formulas and properties of Laplace transformations. Formulas are here and the properties, three properties are here. So we are going to work with the second property. This is actually called operational property according to the reference book. Okay. It is called shifting property. So what shifting property says is that we know that Laplace transformation of f of t is f of s. So what if we have Laplace transformation of e power at f of t? It will be f of s minus a. So we are coming up with a new property. So please don't be confused with this formula. Suppose we have Laplace transformation of e power at. We know it is 1 by s minus a. Still, the same thing can be regenerated by this way. E power at times f of t times 1. So f of t is here 1. So we can also think about like that. But don't be confused with the formula here. Actually, this is the property and e power at f of t is the formula. So suppose let's directly work with some problems. Then you will understand what we have to do. Let me think about one problem. Let's take one problem from reference book. Yeah, I have found one. Question number 7. You can see Laplace transformation of e power t sine 3t. What will be the result? We don't have only e power t. We don't have only sine 3t. We have the combination multiplication part. Laplace transformation of e power t sine 3t. So let's solve this problem. The problem is we have to evaluate Laplace transformation of what? E power t sine 3t. Can you see my screen?
Yes, sir.
Okay. So you might be wrong if you solve separately e power 3t and Laplace transform of sine 3t. This is not same. You know that Laplace transformation of e power at is 1 by s minus a. Here a is 1. So you might be confused with this result. And Laplace transformation of sine 3t will be 3 over s squared plus 3 squared using this formula k over k s squared plus k squared. So this is not like that. If you are doing so, then you are wrong. Have you understood that this is not the right way to solve?
Yes, sir.
Okay, so don't do that. Actually, these are separate problems, different problems. So you can see we don't have any formula like that. Combination of e power at and sine kt. But we are lucky that we have the second property here. So it is going with this property, Laplace transformation of e power at f of t. So try to note down the value of a. Compare this one with this. Laplace transformation of e power at. What is the value of a here?
1.
A is 1. So that is the reason behind why I have mentioned the constant a and k. I can also write cosine at, sine at, but instead I have written kt. So actually the letter has a symbolic meaning. So here automatically you can understand that a is 1. But for sine, cosine, hyperbolic cosine, hyperbolic sine, I have used the letter k. So what is the value of k here? Sine kt, k is
3.
3. Okay. So these are our three values that we have found. Now you can have a look on the property. At first we have to solve. You can see f of t is here. We know Laplace transformation of f of t is f of s, and that f of t is also here, f of t. So that means this f of t and this f of t are same. So please try to understand. Here, comparing with this given question and the property, what is f of t? Let's also write the information. F of t is which one? Sine 3t,
Sine 3D.
right? Okay.
Yes.
So the shifting property is telling us that first solve for this. Laplace, find the Laplace transformation of f of t at first. So I'm going to note down the steps. Step 1, compare with, let's say this is equation 1. Compare with equation 1 and find a k. You will not get k always, because sometimes we may have here some other functions. Okay. So let's say we are getting all the informations. We are finding all the informations, and also we have to note down what is f of t. Step 2, In step 2, we have to evaluate what is the Laplace transformation of f of t. Obviously, it will be f of s. Then, in step 3, input s where you have input s minus a where you have s, and a is coming from e power at. So that means what you have to do, you have to input s minus a in lieu of s. Let's say this is equation 2 into in equation 2. That will be the result. That will be the final answer of this problem. Laplace transformation of e power at f of t is actually instead of s. So instead of s, we are writing s minus a. F of s minus a. So have you understood the algorithm?
Yes, sir.
So our step 1 is done. We have found the value of a, what is the function, all these are here. Let's go with step 2. So in step 2, what do we have to do? Step 1 is done. We have to find the Laplace transformation of f of t. That means sine 3t, right?
Yes, sir.
So Laplace transformation of f of t is f of s. We know we have to do by this way. So that means since our f of t is sine 3t, so we are finding this one. So what will be the Laplace transformation of sine 3t? You know already the result. Use this sine kt. Laplace transformation. Result will be k by s squared plus a squared, right?
Yes, sir.
So it will be 3 by s squared plus 3 squared. Have you understood?
Yes, sir.
So try to listen carefully and understand. This shifting property is very important in final exam, for final exam. So 3 squared. Step 3. What we have to do in step 3?
Inputting s minus 1 যেখানে আছে সেখানে s.
Yeah, inputting s minus a. So s minus a. A means s minus 1. Here is a. So in the place of s, let's say this is equation 2, or no need to give any equation number. So the result we have found in step 2, in that part we are going to replace s by s minus 1. So in right side you can see we have 3 plus 3 squared. Here is s. So instead of s, let's write s minus 1, and we have squared. Okay, so this is the result of this. So Laplace transformation of e power t sine 3t is actually this one. So you will get again a clear concept if we solve another problem. So any confusion here?
স্যার তাহলে স্যার আমরা ইটিটাকে ইউজ করতেছি বেসিক্যালি এর ভ্যালুটা বের করার জন্য জাস্ট।
Yeah. So that means the result can be written in simplified form 3 over s negative 1 squared plus 9. That is the result of this, where we have a function f of s minus a in f of s minus a form, in f of s minus 1 form. So I think you have understood. So please try to have a look closely in the given function. Can we apply the direct formula, or is it going with the properties? So whenever you have a question from Laplace transformation, please try to have a look closely on the question so that you can easily get the idea which parts we have to do to solve. So let me take another problem so that you can understand. Suppose let's say, let's take from here. Question 4. Laplace transformation of t power 10 e to the power minus 70. I am taking a random problem from this exercise so that I can make you understand about the translation or shifting property. Okay, so t power
So can
10,
we do the 11? I mean, ওইটা স্যার ফ্র্যাকশন আছে।
which one? This one?
So
Question 10.
11. So 11.
11.
Yes, sir.
This is not going with that property. It is from
Okay.
inverse Laplace transform. See, it is a problem from inverse Laplace transformation, right?
Okay, sir, got it.
So we are not ready still now to solve inverse Laplace transformation. I am coming up from the very basic concepts. Okay.
Okay, sir.
So let's solve question 4. Actually, in this exercise, all the problems are given. So that's why you were saying that let's solve 11, let's solve some other problems. But the thing is, we are just learning the property, and gradually we can move. We can be able to solve question number 11, not only 11, all the problems whatever we have here. Okay, so no need to worry, we can solve all problems, but gradually we have to solve. So have a look on question 4, t power 10 e power minus 70. I am taking this one, Laplace transformation of t power 10 e power minus 70. Have a look into the second property that we have. We have the property Laplace transformation of e power at f of t, that is actually f of s negative a. At the same time, I am trying to show you the third property also. See the third property, Laplace transformation of t power n times f of t. Second property is e power at times f of t. Third property is t power n f of t is equal to negative 1 power n d power n ds power n. That means n derivative in terms of s of f of s. Can you see the screen?
Yes, sir.
So the similarity between these two property can be easily understood, that both properties, property 2 and 3, are dealing with multiplication type problems. But on the right side, the result is coming up with different functions. So let's also write the third property. This is the second property, and this is the third property. And you know what is the first property? First property is the linearity property. If you have summation and subtraction and constant, constant can be pulled out, summation terms can be separated, subtraction terms can also be separated. So now Laplace transformation of t power n f of t. It is minus 1 power n dn ds power n. That means nth derivative in terms of s variable, Laplace transformation of f of t. And this Laplace transformation of f of t is actually f of s. Okay.
Okay, sir.
Okay. So try to understand. We have this problem. This is going with both property 2 and 3, because if we have a look on property 3, it is going with this one, t power 10, t power n, f of t. F of t is e power minus 70. If we try to understand with property 2, we have e power at times f of t, e power at times f of t. F of t is this time t power n, t power 10. So we can solve the same problem by both property 2 and 3. But now my question is, which property can be used here? By first sight, we can see our subconscious mind may suggest us to use the third property, because we have t power 10 and t power n f of t. This is f of t. So which property can be applied, 2 or 3? Both property can be applied, but which will be the fastest way to solve?
So 3.
If we go up with 3, so try to understand. Here n is 10, so d10, ds10. That means suppose you have finally u by v form. So how many times you have to differentiate? 10 times. First time differentiation, second time, third time, fourth time, up to 10 times. So this will be time consuming. Okay.
Yes, sir.
So in Laplace transformation, you have to understand which property can be applied to solve. So at first sight, we can understand that the third property may be applied, but to save our time, what we can do, we can make it similar to the second property. And the second property comes up with e power at first, and this is f of t. So we can easily solve. Now have a look on the steps. Step 1. What is step 1? Step 1 is to,
comparing and finding a and k.
yeah, we have to find the information. So here a means minus 7. F of t is t power 10. So this is step 1. What is step 2? Step 2 is to find the Laplace transformation of f of t. So our f of t function is t power 10. So Laplace transformation of f of t, that is t power 10. So you know the result. What is t power 10? T power n factorial by s power n plus 1. So it will be 10 factorial over s power 10 plus 1. That means 10 factorial by s power 11. And finally, step 3. So what is step 3? Step 3 is to input s minus
S minus
a.
A.
That means s minus a is minus 7. So minus 7. That means s plus 7 in the place of s. Have you understood?
Yes, sir.
So, so that means from here we can write the result of this Laplace transformation will be 10 by 10 factorial by s power 11. Where we have s, we have to input s plus 7 power 11. So this is our answer. Okay, have you understood?
Yes, sir.
So follow the process. So this is what the linearity property is and the shifting property is. So let's work with the multiplication property, multiplication by t power n property, this one. And by this we can say we have the power to solve any kind of Laplace transformation problem. You can try by yourself. So I will try to give another session tomorrow, maybe at before noon, so that I can discuss the inverse Laplace transformation part. Okay.
Okay, sir.
So uh, let's discuss now the third property. So property 3. It is multiplication by t power n property. Again, the process is same. If Laplace transformation of f of t is capital F S, this is our general notation, then what will be the case for Laplace transformation of t power n f of t is minus 1 power n nth derivative in terms of s variable Laplace transformation of f of t. Okay, so let's solve one problem by using this part. Suppose let me think about a problem so that it goes with this property. Suppose we have Laplace transformation of t squared cosine, let's say sine 4t. Okay, so Laplace transformation of t squared sine 4t. So again, at first try to understand which property will be applied. Property 1, property 2, property 3, or directly the formulas. Can we apply the direct formulas here? No, because here we have just a formula for t power n. We have just a formula for sine kt, but there is no such formula for this. Whenever we have multiplication of t power n and sine 4t, but we have the property. this one. So using this property, we can solve. So at first sight, what we have to do is step 1. In step 1, try to find f of t. In step 2, and also in step 1, try to note down the value of n. What is the value of n? These are the informations we need at step 1. In step 2, we have to solve this Laplace transformation of f of t, and it will be obviously f of s. And now finally, step 3, we have to use this technique. Once we have f of s from here, then we have to differentiate. And here, all the formulas of math 110 are coming, because math 110 deals with differential calculus. So let's work with step 1 at first. What is the function f of t? Compare with the third property.
Sine 40.
Yeah, thank you. So it is f of t is sine 40. If we compare with t power n f of t, then obviously f of t is sine 40. And what is the value of n? N is 2. So this is the information what we have from step 1. Step 2. Step 2 is to solve the Laplace transformation for f of t. So Laplace transformation for f of t, that is sine 4t. What will be the result? We have the formula k over s squared plus k squared. So here the value of k is 4, isn't it?
Yes, sir.
Yes, sir.
So 4 over s squared plus 4 squared. So we can also simplify one more time. It is 4 over s squared plus 16. So let's go with step 3. Step 1 and step 2 is done. Actually, why we are going with property 3? Because we don't have any direct formula for t power n times f of t. So that's why this differentiation rule is coming. So step 3. Step 3 is to use this way. So Laplace transformation of t squared sine 4t. Okay, let me take another piece. So it will be, let's apply the right side formula, minus 1 power n. So here n is 2, minus 1 power 2. Do you understand which part I'm
Yes, sir.
talking about? Yeah. D power 2, ds power 2, and the Laplace transformation of f of t. Laplace transformation of f of t. already we have the result, 4 by s squared plus 16. So our question is to solve this one, so it will be equal to the right side. So let's try to solve. Minus 1 squared is actually plus 1, so no need to write plus 1. Here we have d squared ds squared 4 over s squared plus 16. And now what we can do, we can at first differentiate for one time. 4 s squared plus 16. You can easily understand that we have to differentiate 2 times. So here we have split up the differentiation. So dd is, now you know the property of differentiation, that is differentiation of, let's say, u by v, that is v squared v dds of u minus u dds of v. So let's say the upper part is u and the lower part is v. Can you remember this formula? So v squared in denominator, v dds of u negative u dds of s squared plus 16. So dds s squared plus 16 whole squared. You can see the derivative of constant 4 is 0. 0 times something is 0. Negative 4. Derivative of s squared is 2s. Derivative of 16 is 0. So that means dds of minus 8s over s squared plus 16 whole squared. Do you have any confusion? We are just differentiating.
No, sir.
So we are just differentiating here. Now minus 8 is constant. We can pull out minus 8 here. So minus 8 dds of s squared plus 16 whole squared. Again, it is of the form uy v. So again we can do the same thing. So minus 8 v squared. So v is s squared plus 16 whole squared and it's squared. Do you understand? V squared. So it will be s squared plus 16 whole squared whole squared. So v dds of u, that means upper part, negative u dds of v. So minus 8. Okay, if we simplify the denominator, what will be the result? Power 4, right?
Yes, sir.
So s squared plus 16 whole squared and differentiation of s, this one is 1, negative negative s. Okay, here we can also simplify because we have a plus b whole squared. So a squared plus 2ab plus b squared. Yes, differentiation of s to the power 4. Result will be, what will be the result?
4s cube.
4s cube. 32 s squared. That means 64s. And differentiation of 16 is squared. Since it is constant, so it is 0. So finally, the result is in our hand because in left side, in Laplace transformation of t squared sine 4t, this is actually this one. Now you can also simplify this result so that you can have good equation. So this is the thing. Okay,
Yes, sir.
suppose you have to evaluate Laplace transformation of e power 2t plus t squared plus, let's say, t e power 3t plus t sine t. So can we solve this one?
Yes, sir.
How?
Linearity
At
property
first,
is
we can
fine.
apply linearity property. At first, we can apply linearity property. So Laplace transformation of e power 2t, Laplace transform of t squared, Laplace transformation of t 3t plus Laplace transformation of t sine 3t. Now, whatever single part we can solve, let's solve first. So this is going with directly the formula. Laplace transformation of e power at is 1 over s minus a. So it is 1 over s negative 2 plus Laplace transformation of t squared t power n factorial by s power n plus 1. Right? So it will
Yes, sir.
be 2 factorial. That means n factorial by s power n plus 1. So 2 factorial by s power 2 plus 1. In short, s power 3 plus, have a look here. This is the multiplication term. So we can reorder this with second property. And here we have t sine 3t. So somehow for solving the first Laplace transformation and second Laplace transformation, you are getting partial marking. You are getting partial marks. And now we have to solve this and this. So can we solve this? This is our second property. And this is our third property. So you can use one equation number here. So here you can say now Laplace transformation of e power 3t can be solved by property 2. So you can easily have the result. Let's say the result is written with equation 2. And again, Laplace transformation of t sine 3t can be solved by using the third property. Here t power n, t power 1. So the value of n is 1. So the result can be numbered with equation 3. So now finally use 2 and 3 in equation 1. Replace this and this with the answers. So this is how you can solve Laplace transformation, complicated Laplace transformations.